I hope he's okay. He was supposed to return that day only. Anyways, I'm just recording all the classes. No problem. I'll send it out to him. So today we'll be finishing this chapter. Okay, not this chapter. This topic of liquid drop model. Let us recapture that briefly. Let me present my screen because it's been, I think, yeah, Saturday also. There was a Saturday. I don't have classes. There was a bit of a short vacation kind of in between. Yeah, can you see my screen?
Yes, sir.
Okay, good. So let us recapture. We were discussing the first topic of the second chapter called nuclear models. We saw what a model is in general, just a representation of the actual thing. Sometimes maybe that actual thing is not feasible to be realized in its totality in reality. Partially we may get some hint, some things we are guessing based on that. Okay, so a model would help us. Like we saw some models we have discussed in our earlier days, like pump sorry, plum pudding model, uh, Rutherford atomic model, Bohr's model. Then we jumped into nuclear model, which tries to explain some of the phenomena which is visible based on several theoretical descriptions and other theoretical edifices, but not. I mean, there's no single model discovered till now which can explain everything satisfactorily, all the phenomena of nucleus. So we began with some questions which led to the motivation of forming different nuclear models. Like first one was the consistency of the consistency, not constancy rather, of the binding fraction in this region. It doesn't look like a straight line which I just draw, but yeah, it was more, it looked like it was more or less constant. Why? Certain atomic numbers and neutron numbers which led to tremendous stability. I mean, with respect to its neighboring nuclei, these nuclei showed very high binding energy per nucleon values. Why was it so? And when it was investigated further, it was found that either the nucleon number or the proton number or both were equal to 2, 8, 20, 28, 50, 82, or 126. These are called magic numbers. Let me tell you one thing in this regard. I think I missed that out. If number of neutron and number of proton, if both are equal to magic number, okay, just a minute. I have a writing pad today. I mean, I downloaded an app. You can note it down. I'm just telling you that uh, if both the atomic neutron number and proton number are magic numbers, then that nuclei is called doubly magic nuclei. Okay. Let me try to join the meeting. Give me a moment. Just a second. I'll just stay in the meeting from another account. Okay. So, yeah, I'll discuss it later. So, another motivation was, what is this thing pop up every time? Yeah. Why these nuclei rather, they are excessively stable? Why, like atoms, nucleus also is found to exist in certain quantum states, and also it is most probably to be found in the ground state all the time, most of the time rather, and it can traverse to any excited state and stay there for some time. And why sorry, certain radioactive nuclei, or certain nuclei rather, they are alpha and beta emitters. Though alpha or beta, none of the particles are found inside the nucleus, and we know that radioactivity is a nuclear phenomena. The reason being, there is formation of new elements in the process, and new elements means a nucleus being the identity of any specimen. It is pretty much obvious that there has been some change in the nucleus, not the extraterrestrial electrons. Hence, radioactivity is a purely nuclear phenomenon. Why alpha and beta particles are emitted out of the nuclei? Then we saw there are some models. We just went through the names: liquid drop model, shell model, collective model, optical model. In our syllabus, we would be discussing the first two only. Liquid drop model, we saw that how the nucleus is being compared with the liquid drop. Many analogies were drawn. Slowly, we went on to derive three terms. Okay, and these three terms were pretty much, I mean, the analogy was very much pertinent, legitimate. And then from there, we found the binding fraction of the nucleus. Then we tried to compare with the empirical graph, which we have from experimental data. And then we used that Desmos graph calculator. I hope you remember this one, Ayush. We saw the nature of different uh, graphs. Remember?
Yes, sir.
I don't think I
Yes,
should
sir.
repeat it then. I'm not going through that anymore.
Yes, sir. Yes, sir.
Fine. Okay, good. And now, next we saw that this thing was very close to the empirical graph, which is expected, but still there was some huge limitations. Like it was observed that there are many lighter nuclei. Lighter means, I said that the mass number we can take it less than equal to 20, with which are having same number of neutron and proton, like He24, helium 24, 2 proton 2 neutron. They are extremely uh, stable. Not only that, helium being an inert gas, that's the reason, but other non-inert gases, non-inert elements also showed this behavior. And it was also seen that naturally there is a huge there's an abundance of nuclei which has even number of proton and even number of neutron compared. And on the contrary, there is a huge, dearth or rarity of nuclei having odd number of neutrons and protons. And these things need to be addressed straight away. So we cannot, just shrug away these things that are let it be. No. Hence, what the modifiers of this model suggested, now we need to call for pure quantum mechanics. That is, the terms or the additives that we would be calling for now, they are purely quantum mechanical. We can't compare something with the volume of a water drop, or the case of passengers in a overcrowded bus. No. So the first term, that's the, I mean, from here onward, we are beginning today's discussion, is called the asymmetry energy term. See, these terms descriptions are not too much in the syllabus, but I'm still trying to go through. I think I'm audible properly, Ayush. Am I audible, Ayush?
Yes, sir.
Okay, okay.
Yes, sir. Yes, sir.
Because out here it's about to start drizzling, and network goes down when it's raining. Anyways, so the asymmetry energy term, I'm trying to explain it very simply, very lucidly. I try. So it is imagined that the nucleons inside the nucleus behaves as a potential well. I think you remember what is a potential well. You studied a one-dimensional potential well, isn't it? Remember that in quantum mechanics?
Yes, sir. Yes, sir.
Yeah. So basically, the well is what? I mean, someone has fallen in a well. It's impossible to climb the well. That is, the walls. they represent the boundary. Within it, you are free. That is, within the well, what was happening there? The potential is zero, and at the boundaries, potential is infinite. Hmm. Okay. And now the neutrons and protons, they are spin half particles, they are fermions, and we definitely have to apply Pauli's exclusion principle, which does not allow us to put more than two protons and or two neutrons, that is not more than two fermions in an energy level. I hope you remember this one.
Yes, sir.
And those two maximum two things allotted, they will also be of different spin. That is actually the Pauli's exclusion principle, which said that it's never possible for two fermions, two electrons to begin with, to have all the four quantum numbers as same. And this is the conclusion of that. Hmm. Actually, the maximum number of particles that can be allotted in a level, if the spin of the particle is s, the general formula is actually this one. You should keep this in mind for your jam exam. If s is the spin, then maximum you can fit 2s plus 1 particles in that state. Okay, here s is half, so 2 into half is 1, 1 plus 1 is 2. Okay, later on in your jam exam, you will come across questions previous year where they ask questions about linear harmonic oscillator uh, with particles of spin 3 by 2. Then they ask for the degeneracy. Okay, anyways, so I went across many resources, different people represented differently. So see, the blue color ones are the neutrons, red color ones are the protons. And the states have been arranged together. I mean, these are the neutronic state, these are the protonic states. Okay, and the gap between the energy levels is say delta E. Fine.
Yes, sir.
So see, in this situation, the number of neutron and number of proton is same. That is, Z minus n is 0. Now you would be studying this thing in your coming days, beta decay. So inside the nucleus, there is continuous conversion of proton to neutron and the other way around. So a neutron is converted to a proton via a beta minus decay. We'll study it later. So see what happened now. Previously we had 4 neutron, 4 proton. No difference between the two numbers. Now one neutron has been converted to one proton. So now see, number of neutrons is uh, 3, number of protons is 5. So what is the difference in the two numbers? It is 2. Are you getting it?
Yes, sir.
More importantly, now one more proton is in the state and there is an additional increase of delta E energy. Why? Because of this. That is has been promoted to a higher state and the gap is delta E. Clear?
Yes, sir.
Now another conversion may happen. Then another neutron will be converted to a proton. That means the difference between the two numbers is how much now? 4. And the total increase in energy, I mean compared to this thing, okay, when things were symmetric, equal number of neutron and proton, compared to that we have now an increase in energy of 2 delta E. Now you can continue this trend. So one thing is noteworthy: when the change in neutron and proton number is 2, I have taken the modulus, the magnitude of the change matters. Then what is the change in energy? Total shift. Shift means change in energy. You can think in terms of delta E. How much it was? Only delta E. So the total shift of energy in terms of delta E is how much? 1. Did you get this thing? Why is it 1?
Yes, sir.
Yeah. Now when the change is 4, when the change in neutron and proton number is 4, the shift is found to be 2e. Hmm. I'll explain the third column. When the increase is 6, it will be found to be 5, and so on. Now they tried to um, get a mathematical model of this. They tried to uh, find the underlying trend, how I can mathematically write this variation. So after many trials and errors, they found that if we uh, you know see, this is the change which is visible, but how to relate this change with z minus n? Z minus n is, you can think it is the uh, independent parameter, and energy shift is the dependent parameter. With change of this one, this change is happening. Are you getting my point?
Yes, sir.
Very simple. Like you have a column of x, you have a column of y. They have asked what is the relation between x and y. So with this thing, n minus z whole squared by 8, you can see nearly the values are close. Okay, not exactly, but there is in many occasions, on many occasions you can see the numbers are exactly matching. On some occasions, it differs by 0.5. So it was approximated that the energy shift approximately is n minus z square by 8 times delta E. Just they tried to give a approximate mathematical expression to this one. Okay.
Yes, sir.
Now it was found by experiments that the change in delta E, this thing, is found to decrease with 1 by A. It was observed mathematically, not mathematically, experimentally it was found. So they said that okay, fine, delta E varies with A, and capital A is the you know important. I mean, the binding energy is written as a function of A, isn't it? So they have expressed it like this. The minus sign is due to this decrease thing. So minus A, another constant, then n minus z whole square. 8 they have taken inside this constant, and delta E they have represented in terms of 1 by A. So that is the asymmetry energy term. I hope you understood why, how it is happening. Any
Yes,
doubt?
sir. No, sir.
See, I must admit this is a very simplistic explanation, but I think at this point of time, you don't require any in-depth explanation than this. If you're eager, you can go through the internet. We are really short on time this time. Okay. Anyways, and this thing, why is it called asymmetry? You can see what is the symmetry condition when n and z are equal, isn't it? So what is the symmetry thing when n equal to z? In that condition, n minus z is 0. So this thing will pop up only when n and z are unequal. When n is equal to z, this term won't turn up. Okay. Now the last term which they tried to add is called the pairing term. Before that, some statistical data, some statistics for you. I said that one motivation to work forward is the this thing, why n and z equal to cases for lighter nuclei particularly, hmm, they are found to be stable. So you can see now this term is a negative term, that is it contributes to some decrease in the total binding energy, right? That is why it's minus sign. Okay.
Yes, sir.
Now if n and z are equal, then this thing is 0. That means the binding energy from which the term which was getting making its which was making it smaller, now that thing is no more there. That means the term is now, I mean, it's increased in place of decreasing. That's why for these cases the binding energy is particularly high. Now the second thing, the natural abundance and rarity. See, I said even are very abundant. See, the nuclei These data might have changed recently, I don't know. You can check the internet, but I don't think there would be huge change in the relative values. So the neutrons, the nuclei having even neutron and even proton, we denote it by even. Okay, we don't see even neutron, even proton. I have written here for uh, your ease of understanding. When nucleon number is even, now how can a number which is a sum of two numbers be even? Obviously, when two numbers are even, a is equals to n plus z. When n even, z even, then only a can be even. So the number of isotopes of those even nuclei is 165. These are naturally occurring isotopes. Now, when can A be odd? When n is odd, is even, or z is odd, n is even. Number of stable isotopes of those nuclei is found to be 105, less than the previous one. The striking thing is that when nucleon number is even, and the reason behind that is both n and z are odd, only 4 naturally occurring isotopes have been found. So why is this disparity? Why is this thing happening? Odd is only 4, even is 165. Nearly, not nearly, more than 41 times. 41 times 41 is 164. Sorry, 41 times 4 is 164, is 165. So now this description is very difficult to be explained at this level. So this thing was taken care of by introducing a parameter called delta pair. Now for even thing, delta pair is taken as minus delta. For odd even or even odd case, delta would be 0, and for odd case, delta would be plus delta. Okay, and by trying to fit this with the experimental data, the best fit gives this expression of pairing energy, delta pair by a to the power half. Okay, yes, it's enough for you to know this expression. Okay, so this is the total formula for you. I have written it in terms of binding energy, not the binding energy fraction. You can do it by dividing by a. So this is called the very important semi-empirical mass formula by Bethe and Weizsäcker. Sometimes it's called the Bethe-Weizsäcker semi-empirical mass formula. Okay, mass means yeah. Why is it called mass? We'll just if time permits, we'll do one application. From here, we can get the mass parabola thing. So why is it called semi-empirical? You can see partially some terms in this expression, they have come from assumptions, and some terms have popped up from experimental data. Okay, like you see the last two terms, these things were called due to the fact that we could not match the experimental phenomena or the experimental observations with the theory. And the first three terms you can say they are much more theoretical. So it is called semi-empirical. It is partly empirical, that is partly based on experimental data, and partly it is based on some theoretical assumptions. Okay, I would suggest you to mug up this formula. Fine.
Yes, sir.
I just taken a screenshot of a Google picture here because the typing the entire thing was getting horrible on PowerPoint. Yeah. Now, if you want to fit this formula, I mean the data out of this equation into the actual data, you have to calculate the parameters like I told, only chi-square fitting, where you fit the points on a straight line. Accordingly, you find the parameter values. So by that, you can find this. I mean, these parameter values were found to be this one. Okay, this is very important from your interview perspective. I told you before also one day that they may ask you that how is Ev coming to be nearly 16 million electron volt. So students, what happens, what comes to the mind is that putting the values of these things, like, yeah, and so start putting these values. No, that is not everything. These are the fit parameters. You will say that by obviously use of softwares. It's a very complicated graph, or maybe by some mathematics. It was found that for these values of the parameters, we get the actual thing. We get the actual empirical curve. It's so sometimes also called the liquid droplet model. Yeah, I got this picture. Everything has been incorporated in this picture. So you can see these all the terms have been drawn in terms of uh, graphs. Actually, there's some mistake here. Not mistake. Along this way, they have plotted EB by A. So this one you expect. We saw this that AV is a constant, so it would go like a straight line. We saw that a to the power 2/3 has a trend like this, minus 2/3 in fact. A to the power 1/3 has trend like this. A to the power, sorry, a to the 1 by a, that is this thing, minus 1 by a in fact. It goes like this. The last term is another constant delta. It will appear if you, not constant, there is also a by, I think would be a to the power 3 by 2. Okay, so this is the overall this is from a research article. So that is the contribution of each and every term. Don't worry, these things no one will tell you to draw on the exam, but it's for your own personal satisfaction. Okay, so understood, Ayush?
Yes, sir.
I'll share this PPT on Moodle also. You can copy these things if you want. Okay, fine. So what are the achievements of this liquid drop model? And we must say that the building blocks of this liquid drop model was very, very classical, isn't it? Starting from surface tension, latent heat of vaporization, all these things. It could explain many things. That it could explain that the binding energy of lighter nuclei can be explained from here. Fission and fusion process. These things are not in the syllabus. I can give you additional learning material. You can see how these things are explained. Okay, basically same thing. Liquid fission and fusion. Fission, I can tell you at least that it's like when the drop becomes very heavy, becomes heavier and heavier, it breaks down into droplets. Okay, with that analogy, they have explained nuclear fission. If you remember that documentary which we showed on Einstein's birthday, 14th March 2020, remember one lady was there, last story, Lisa Meitner.
Yes, sir.
There she was in, after the World War broke, they just, sent her away from Germany. She was in Austria, I think, with her nephew skiing in the snow. There she could suddenly, uh, she got the Eureka moment when she could explain nuclear fission with comparison to a liquid drop. If you have the movie, you can see it. It's on YouTube available. Okay, E equal to MC square. There is something else also as the second subtitle. I don't remember. Hmm. So there she could explain nuclear fission with the cleavage of water droplet when it becomes heavier. Same thing here also when the you can see that where this is with radioactive elements, it's feasible to achieve. And it could explain the radioactive decay and again fusion and fusion processes. But there are some limitations. Still, despite of all these things, it could not explain us why magic numbers. I mean, why particularly for 2, 8, 20, 28, 80 to 126, number of neutron and proton, or both. The isotopes are very stable. Neither it could explain excited states, nor it could account for the nuclear spin. So these are the limitations of the liquid drop model. Yeah, this may be asked in the exam. So the solution to this one is obviously a better model that is called the uh, shell model. We'll discuss it later. But now I think we should do some numerical problems. If you have any doubt, you can ask. Else we can move to some numerical problems.
Yes, sir. No doubt.
No doubt. Do one thing. Uh, just copy. You can copy these equations or take a screenshot. I think copying would be better. At least copy question number 6 and 1. Copy these two. Just tell me. I'll show you how to work out with these problems. Number one, you need not to copy. Just tell me the answer yourself. The semi-empirical mass formula for binding energy of a nucleus contains a surface correction term. Very true. Now they have asked that this term depends on mass number of the nucleus. Like how much? A to the power what? What is the which one is the surface term, Ayush? Which term accounts for the surface energy term?
Sir, a to the power 1 by 3.
Which term? I mean, why is it 1/3? No, I am asking you the term. Tell me the term. There are five terms total. Which term you're talking about? See, the question is very important. They have told you binding energy. Okay, that is BE. They're talking about this term. This term depends on surface, right?
Yes, sir.
Isn't this the surface energy term? Okay, now I'll tell you how to try it. Achha, now you copy question 6 and 1. Then tell me. Then I'll use my digital writing pad software that I installed today.
Yes, sir. Done, sir. Copied, sir.
Yeah. Both the questions.
Yes, sir.
Question 1 also you copied.
Yes, sir.
Okay, fine. Achha, now I'll just stop sharing this screen. Sure, now I'll share this screen. I hope it will work well this time round too. Yeah, fingers crossed. Yeah, I think you can see my screen.
Yes, sir.
Yeah. So this is the software that I have installed on my mobile phone. So what was the first question asking us? It was asking mm, surface energy term. Okay, by chance you forgot this in the exam. So surface energy term, definitely the term would be proportional to the area, surface area, isn't it? What is the shape of the nucleus, Ayush, that we are assuming? What shape of the nucleus are we thinking in this model?
Sir, drop, sir.
No, no, geometrical shape.
So, circle.
Circle or what? Circle is two-dimensional.
So, sphere.
Sphere, exactly. That is, what is the area of the surface area? 4 pi r square.
Yes, sir.
Now, yeah, these things you have to keep in mind that, sorry, that r looks like this. A to the power 1/3. Okay. Now this 1/3, this thing you will put here. That is, it is actually proportional to what? R square. That is, R is again related with A as to the power one third. So that is the actual trend. Okay, so if you forget this thing in the exam, at least this term and the even the Coulomb term also you can remember.
Yes, sir.
Okay, yeah, and if they ask you the binding fraction, read the question. Okay, if it is binding energy per nucleon, the binding fraction, then that would be proportional to. I mean, for the surface energy term, it will be proportional to a to the power. Sorry, bring it this way. Yeah, a to the power two third by a, which I think is equals to a to the power minus one third. I think this was also given in one of the options. So they tend to confuse
Yes, sir.
students. They give all the options. Acha. So at least for the first three terms, you can remember everything. Let me give you the brief thing. The volume energy term, that is proportional to volume. Volume means R cube. It is simply proportional to A. Surface energy term varies as R square. It is proportional to A to the power two third. And the Coulomb term, that is proportional to 1 by R, that would be equal to A to the power minus one third. Okay, you can keep these things with you, this formula. Okay, yes, some handy formula.
Yes, sir.
Okay. Yeah, what was the next question? It was related to, yeah, that's also very easy. What was given? It was given that uh, cop- oh, copper 6429. This isotope has a radius of 4.8 into 10 to the power minus 13 centimeter. So they have asked to find the radius of magnesium. See, first of all, the unit you need not to change the unit. It's both in centimeter. There was another part to this question, but this part is according to your syllabus. Hmm. These are gate exam. Once you enroll yourself into a postgraduate degree, you can appear for the exam. Anyways, any idea, Ayush, what formula we can use? Any idea, Ayush?
Sir, I'll read the question once more.
Yeah, just you have copied it, right? Did you copy or you didn't?
Yes, sir. I copied it.
Yeah, yeah. Read it once yourself.
So R is equal to R naught A to the power 1 by C.
Yeah, very good. So that's our formula that will help us. So we know that R equals to this R is written as small letter according to all the most of the books. Doesn't matter. It's a constant after all. Yeah. Now it is safe to say that R is proportional to one third. Right. That's the formula. So now what we have? We have copper first. So let me write it in this fashion in comparative ratio mode. R copper by R magnesium would be equal to A copper, A magnesium to the 1/3. Clear? A suffix mg. You can write A1, A2, whichever you like.
Yes, sir.
It's an MCQ exam after all. No one is going to see your rough work. It's up to you. But still, in exams, we often tend to be confused by our own writing sometimes. So, whatever you write, at least you don't get confused in the exam. So, from here, we know that R copper is given. How much is the value of copper? 4.8. 4.8. See, you can write 10 to the power minus 13 also. It's a ratio. Okay, that thing doesn't count. Still, write it by R of magnesium. So that is equals to, what is the A? What is A for copper? What is the value of A? Yes, Ayush. What is the value of A for copper?
Yes, sir.
Is there in the question only.
0.8 into 10 to the power 13.
No, no, no. A, capital A. That is R that you are telling. R we already put here. R is already here, isn't it? I'm
64.
asking this value. 64. Yeah,
64.
exactly. 64, right. So 64 is for copper and 27 is for magnesium to the power 1/3. That is, you have to do the cube root of this one. I think you know this. 4 cube is this much. 4 cube is 64. 3 cube is 27. So basically, from here we can see that magnesium's radius is 3/4 of that of copper. That is, our magnesium is 3/4 of that of copper. 4.8 10 to the power minus 13 meter, 1.2, that is 3.6 into minus 13 meter. Sorry, centimeter. I'm extremely sorry. Data was given in centimeter. Did I write meter anywhere else? Check. No. Okay. So your option is 3.6. You can see there was no necessity of putting this 10 to the power minus 13 here. You have to keep in mind the order would be same. It's a ratio after all. Clear, Ayush?
Yes, sir.
Are you able to see from this whiteboard? Is everything clear?
So which app you are using, sir?
It's what is the name of this app? Let me check. It's called whiteboard. The reason I
From
am
phone.
use, yeah, from phone only. Yeah, it's my phone.
So do you have a pen or something to write?
Yeah, I just bought it a few moments ago from
Oh, yes, sir.
a normal pen. I'll just show you, send you the picture. A normal is a 30 rupees pen. You can use it at a ball as a ball pen also. I can use my finger as well, but still using a pen like if I write this thing with my finger, I'm writing it with my finger, and I'm writing with this pen. You can see I'm getting a sharper image.
Yes, sir.
I felt that because I saw some of my recordings, things are getting blurred, and you all know that it is due to my network. So sometimes students are feeling hesitant to tell me. So I think this would be good. Sometimes I'll record the page also, but most of the time I can work here. I don't think you're having any problem. Screen is
No,
not
sir.
getting blurred or anything.
No,
Yeah, then
sir.
experiment is going good. And here you have a infinite page expense. You can go as long as you want. You can zoom in, zoom out. You can use different colors as well. I just try to see if I can send you the uh, this class notes also.
Yes,
Just
sir.
see. Anyways, now you do one thing. Let me copy. Try do one
So
thing. I'll
Khan
just
Academy also uses this type
yeah,
of
yeah. No, they are
method.
using something called Wacom digital writing tablet. It is very expensive. It's nearly 10,000.
Yes, sir.
So
This type of method only they use, sir.
yeah, yeah.
Writing
Now
method.
problem is that if you're using a phone, you are not feeling any problem. Here the thing is that like when I'm writing, I have to see, I have to zoom to 35% like that. Then I have to zoom out. So this thing in that writing pad, those tablets, they are nearly A4 shape, A4 page shape. So these things, anyways, I'm not having some that much problem here. Let me type. Let me see. Let me uh, now write this question. Let's see how it works. I'll write it very briefly. Okay, that
Yes, sir.
I'm not writing everything. That the binding energy is given like this: B equals to AV capital A minus AS A to the third. I just zoom out. Let alone. Don't worry. A symmetry 2Z minus A whole square by A minus A. Sometimes pen is a bit difficult to work with. Acha, AC Z square A to the one third. Okay, so this is given. I think it's visible now, Ayush. Can you copy?
Yes, sir.
Okay, so this is what is given. Acha, let me type the question, write the question fully, then you can copy. Acha, where AV is 16 million electron volt MeV, comma AS is also 16 MeV. Yeah, these two values were close. We saw it in that slide also. The symmetry or asymmetry energy term, whatever you would like to call it, is 24 MeV. Now let me write it downwards. And AC is how much? 0.75 MeV. You no need to mug up these values. In exam, they would be giving you. Okay. For the most stable isobar. Acha. Find the most stable. It's an application, okay? Stable isobar. One application of liquid drop model. Isobar, we know that same mass number, right? Isobar with, because this entire binding energy is a function of A, 216. Now I'll just zoom out. Yeah. Oh, I'd have written on the left hand side as well. Anyways, so the question is that you are given an expression of binding energy which looks like this, where the parameters value is this one. So they've asked you that find the most stable isobar with A equal to 216. Simply you need to find the value of Z. That is, you need to find what is the atomic number when A is 216. That is, what is isobar? Different elements having same mass number, right? So when mass number is 216, For the most stable isobar, what is the value of z? Just copy the question and I'll tell you how to do this.
Sir, done, sir.
Okay. So what is an isobar? I am telling same A, different Z. Okay. I think you agree with me.
Yes, sir.
And what is an isotope? Same Z, different A. So here they're talking about the most stable isobar. That is simply you are given a value of A. What is the value of Z for the corresponding isobar? I mean corresponding A, provided that is the most stable isobar. So the condition for this one is this. You have to keep this in mind. For the most stable isobar, as the name suggests, what do we expect? The binding energy is maximum. So simply use this maxima condition. The condition is del B del Z at a given value of A is 0. Why did I put del? Because there are other factors also on which binding energy might depend. But here we are looking into one factor, one variable rather, Z. Simply you are given a function of say x, you are using df dx is 0. Del f del x 0 if it is a multivariate function. Why? Because binding energy is maxima here. I think you agree with me.
Yes, sir.
Now the thing is that you have to work bit smartly. Just go here. Just see where are the z terms present. This thing is a very complicated equation. Just simply see wherever you have z. So I have z
Symmetrical and Coulomb term.
exactly. Now there is another thing. Not always all the terms will be given. You see here only here the Coulomb term is given. The pairing term is not given. Pair term is many times they just keep it off. These two terms are containing z, yeah, with the minus sign as well. So simply when you are doing the derivative, what you will do? Simply do differentiation of the last two terms. Fine. Why should I do everything? There's no point in doing that.
Yes, sir.
So these smart works are required for MCQ exam. Let me change the pen color. Yeah. So this implies that mm, del z of, can put a third bracket. What was that term? Minus asymmetric asymmetry 2z. Is it like this 2z minus a or what it was? Let me check the symmetry term. Yeah, 2z minus a whole square by a minus ac z square by a to the one third. This is 0. isn't it? This is what we would be doing only.
Yes, sir.
Now it's a bit cumbersome thing to do because there are many other factors which you can't simply put zero. I mean, you have to carry all the constant terms also. So here, next thing would look like, next step would look like this: minus asymmetry, that is x squared type, but it's a function of, I'm doing derivative with respect to z. So n into x to the power n minus 1. Okay. Again, I have a 2z. If I do derivative, it would bring 2 the power a, minus the second term is giving me a coulomb fz square. So that would be 2z a to the power 1/3 equals 0. Fine.
Yes, sir.
Okay. Keep in mind, what do we need to find? We need to find that value of z for which it is maximum. Okay. Don't get lost. So big thing. Now you have to just simplify. Simplify. So first term would be minus asymmetric. I have 4 there, right? 4 2z minus a upon ac by a. Okay, something like this. Now this is a minus thing I don't like. I can absorb it with the term in the bracket. You can do the calculation on your own also parallelly. So it would be asymmetric by a 4a minus 8z. 4a minus 8z equals ac 2z by a to the power 1/3. Okay. So you can cancel one. What we have here, 2, take care of the 2, you can take care of that. Okay. Oh, sorry, time is up. Okay, Ayush, you can continue this. I have another class after this one today I'm taking.
Yes,
Okay,
sir.
so you go on and you try to find the value of z. That would be your
So
answer.
can you send the recording to me, sir?
Recording, you remind me once in the evening. I think it takes
Yes,
one
sir.
hour or something. Okay, if I get the recording by the before that, I'll just send you the link.
Yes,
So
sir.
now you have to find z. So I think you
Yes,
are
sir.
comfortable using this one, right?
Yes,
This
sir.
thing. Okay. Okay, then we'll discuss in next class. If you have any doubt, you can ask me next class. Okay.
Yes,
I have
sir.
to
Thank
go
you.
for the, thank you.
Yes, sir.